is a feed-forward neural network basically has input nodes. Each of those nodes is, say, a number, a real number. And it goes through hidden layers, through basically weighted combinations of each, linear combinations, and you get an output at the end. So you get an input vector of 3 items. You run them through a linear transformation or a affine transformation to get hidden vectors. Do it multiple times, eventually you get an output. The neat thing is that because we parameterize our transformations by matrices and linear algebra techniques, there's really efficient ways to optimize the weights and the parameters to get the right output from the inputs. It's kind of a brief high-level view of neural networks and why they're used in industry. So each layer essentially receives an n vector and produces a y vector. This background. And some of this came off the screen. But every layer's output is the weight. It's parameterized by weights, and you multiply by weights and add a base and add the bias vector, apply it to a function, activation function, and you get 3 outputs. So a neural network has multiple of these in a row. And training a network means picking the right weights and biases to get your problem done. So that's essentially neural network, basically step by step, apply this at every step, and then so vectors go in, vectors come out, and then goes until you get the output. So that's the action happening at every step here. It's a multiplication by a matrix and an addition of a bias vector. And that matrix, the vector and the matrix are a parameterization of the network. So let's try running Haskell. This is a naive attempt at writing neural networks Haskell. I actually saw this online. People actually do try this, and it does hurt my heart. But we're going to see why it hurts my heart, but why it's also a nice first step, a naive implementation of neural networks Haskell. So layers represented by things between weights. And like I said, weights are parameterized by a bias vector and a matrix. So if the bias vector has dimensions n, and the matrix has dimensions n to m, then this weight represents a layer from m to n, from m-dimensional to n-dimensional, because of how matrix dimensions and multiplication works. These types are from HMatrix, just from the top-level module of HMatrix. They actually call out to C subroutines using BLAST, so they're very optimal. But we won't worry about the optimization right now. But these are efficient vectors, efficient matrices implemented by HMatrix, the library. And so the networks is a chain of those, right? So this is basically a list. This basically a list that has at least one element. It's a non-empty list, right? If I parameterize this network by a type, it's basically a non-empty list. So the network is either just one output layer, which has a layer of weights to take from input output, or it has weight to another network to produce a new network. And for example, we have, if a network had 2 hidden layers, H1, H2, an output layer, O, it would look like this. Layer 1, weight 2 to the output layer. Any questions about how I structure the networks? It's basically kind of a list type in Haskell. It's a basic recursive list type in Haskell, where each item in the list is a vector and matrix. Notice I have to specify exactly what each thing means, the dimensions. If you're a user writing this, you would have no idea. Like, you have to think about what dimensions of each thing are. So running them is pretty simple using HMatrix. Running a layer is pattern matching on the bias and doing the basic operations. So this is plus and ampersand, or plus and pound sign less than, are matrix's multiplication, addition, and matrix vector multiplication. So you don't think about the details, just this is how you run them. This is how you do the actual linear algebra in HMatrix. If you're familiar with neural networks, you can see the math there, but this is basically how you run the network, run the layer in HMatrix, perform the operations. Running the layer is simple. You just given an input v, you multiply by the weights, you add the bias, running of network is just basically running through each iteration, basically a fold. So it's basically it's a left fold or right fold. This is a anyone know? Is it left fold or right fold? This is a right fold, I believe. So this is we're just folding through the matrix. We can write it using fold if we use a list. So if we use a list initially instead of the fancy network type, this would be just fold R or fold L. So any questions about how I ran the networks? This is just HMatrix syntax for multiplying and adding. This is how we do it untyped. Already, if you're a Haskell programmer, you should be getting a lot of red flags, right? How do you know WB and WN have the right dimensions? How do you know that you can run with the same vector that they all line up? I'm already reading this, I already get anxious reading this. And generating vectors randomly. So we're going to use multi-random library, but it's just basically simple. We can generate random numbers monadically. So HMatrix lets us generate random vectors and random matrices. And the naming is not too intuitive, but just pretend that random vector gives you a random vector given a seed, and uniform sample gives you uniform random matrix given a seed. This is HMatrix's API for generating random things. So to generate random weights, you take two inputs, the input layer and output layer. You get two seeds, create them, and then return them packaged up in W. To make a random net, it's just it's basically replicate. It's basically a traverse, a map M. So you give the input net layers, the input layer size, the hidden layer sizes, output layer size. And so if you want to generate an empty net with no hidden layers, it's just one layer, the output layer. If you want to generate a net with hidden layers, it's just you generate a random layer, generate a random network with the rest of the network, and just cons them together. Any questions here? This is just replicate M if you're useful with This is map M or traverse if you're useful with Haskell terminology. So to generate a random net with no hidden layers, it's just a random layer. To generate one with hidden layers, you generate first the first hidden layer, rest of the network, and you cons them together. It's a basic traverse. We write it out manually just for educational purposes. But if we had used a list, we could just write, this would be a traverse, basically. Now, Haskellers should already be getting anxiety, right? So what if we mix up dimensions for random weights? Look closely at random weights. What if we had used O instead of I there? Everything would be totally wrong. Things would break right away. You wouldn't notice. They wouldn't break right away. When would they break? At runtime, which is even worse. They break at runtime. It'll compile fine. Runtime, you run them, and then things explode. Or they might even not explode. They might be right if you use the same input outputs. It'll test them and they'll be correct. But then when you actually do them with other things, you get incorrect, and it would be a runtime error. And how do you know that the network will line up? Every layer will line up. So what size does this layer, does this function return? Who knows? It's not in the type. We have to kind of infer. It's not in the type. We had to use our minds to think about it, our brains to think about it. GHC won't help us. And how do we know that whatever this returns, whatever this is, will be compatible with this? There's no way. You have to basically assume that whoever wrote the network code wrote it correctly, making mistakes. And I really don't like assuming that people don't make mistakes, because usually I'm wrong. And even worse is when I hate even assuming that I don't make mistakes, because I wrote the code, I probably would make a mistake. I write my hobby code late at night, and that's the prime time for really silly runtime errors. So there's so many ways you can write this and still compile the Haskell things. And how does the user know what size a network expects, right? So if a user this is kind of an end user issue. The type of a network is just network. is this the type of this network? Does this expect a 2 vector or 3 vector or 10 vector, 100 vector? Does it expect a matrix? Who knows? Well, actually, we know it expects a vector because it's a type of run network. But even looking here, this is dangerous, right? So I give a network that expects a 2 vector. How do I know what vector it expects? There's no real way of specifying what, and the user has to basically know or do a runtime check. You can make a runtime check function that checks a network what input it has, but that's a lot of overhead, runtime overhead. The user has to basically either assume that the documentation is correct, that run matrix, that generate network does the right thing. So many things can go wrong. It's just so many things that can just happen. Small things can go wrong along the way.
So
Yeah.
network operators basically blow up if you don't match them.
Yeah. They blow up at runtime sometimes, right? So for these cases, a little kind of a toy example, because in these cases, the runtime errors usually happen the first time you run them. But in other applications, the error might come in an edge case, or in the third time you run them, or 10 months later in production. So in this case, kind of stretch your belief. This is kind of a contrived example, because in this case, the runtime errors happen right away. But in a real world situation with different applications, these errors might happen later. It might be hard to detect. They might be edge cases. Not even unit tests can really help find all edge cases. Or even Haskell's quick check, right? Quick check can't find all test cases, all edge cases. Even normal Haskell tools that we think are better than imperative tools still can't really solve this exactly. And secondly, the fourth thing is a run layer run net correct. We don't really know. I wrote them and they compile. And in Haskell, we want to say if it compiles, it's correct. But here we don't really even know. We can actually there's so many ways to write this that will still compile being correct. The space of implementation is so big. And in Haskell, if your space of implementation is so big, you kind of get a vertigo if you have so many places to implement it and just all of them will type check. It's just not a good feeling for Haskeller, and I hope for you too after this talk. So are they correct? We don't know. They're not verified. The types don't really help us with that. So, and now we're going to do the kind of the big monster backprop, where it's pretty mechanical, but there's a lot of places to mess up. So backprop, I'm going to show the actual code. So we're basically going to iterate through the network. So output layer, we find the gradients and go backwards and return the bundle of derivatives. And in the inner layer, we do kind of the same. We do run a layer, pass down to the next, run the layer, pass it to the rest of the network, calculate the derivatives, and pass back upwards, back propagation. I'm not going to go too much into detail, but can you just see how many ways you can go wrong here? You can give y to run layer instead of x. I mean, you can give any vector instead of x. Logistic, you can actually do logistic x, right? Whatever logistic x, it will still compile, but it would be wrong, and then I might catch it right away. So many ways to mess up here. What if we out product with y instead? Or what if this is a matrix? What if we use the wave matrix here instead? I'm basically relying on my naming conventions to help me, but relying on naming conventions isn't really a safe thing to do in general programming, right? That's like the Hungarian notation fallacy. You can't fix things with just having better names. In this case, there's so many ways to input incorrectly, so many ways we don't know it's right. It might be wrong, things might not line up. What if we put the wrong thing here? It's just so many ways just messing up here that writing it actually took me a while, actually. I actually messed up when I wrote this first time. I messed up a few times, actually, writing this first time. That's how even though I knew neural networks, even though I've been working with them for years, I still couldn't write the first time. I had to iterate through a couple of errors until I got the right notation. So where's the compiler in this? So Haskell, writing Haskell, the zen of Haskell is letting the compiler write your code for you. So how much did the compiler help here? It didn't help at all, really. It didn't, and then the shape matrix didn't guide our programming at all. Ideally, we want the compiler to guide our programming. the shapes of our type, the shapes, which is just a code word for types, right? The shapes should guide our programming, but in this case, they didn't. How much of our program is guided by types of our shape matrices here? Pretty much none of it. And almost all of it was kind of written, all of it is partial, really. And red flags are Haskellers. A Haskeller should always be going to a checklist in your head as you write code. When you write a function, how many ways can you write your function and have it still type check? This is something Haskellers always have in their mind. Because if there's a lot of them, that's when Haskellers get scared because the compiler can't help them. It's kind of a general checklist Haskellers have when running through code. When you encounter a situation where you have a lot of ways to write a function, that's immediately a red flag. That something can be done better or something can be done more safer, or you have to be more careful. How many functions are partial? That's another red flag, right? How many functions are partial? Almost all the functions we wrote are partial. Partial, in this case, means they don't take all inputs, right? So even train is undefined when you put in the wrong input vector or wrong network. They don't match up. Even run layer, up here. Even run layer is partial. Run net is partial. And random weights and random net are not partial, but they could potentially be if we wrote them badly. Or also, in this case, the int can be negative, which it shouldn't be anyways. But we're not going to address that. So int can be negative. Types don't help there. So many ways you can write partial functions. And just being aware of that the whole time is a kind of a Haskell red flag. Haskell checklist should be going through while we're writing Haskell. So how can we approach this and add types to our functions and make things work well and fix all these problems? How can we restrict the parent space of our functions, have the compiler help us write our code, and also make our functions total? The answer is usually type-driven development is add better types. So type alternative. Now instead of HMatrix also offers typed vectors and typed matrices. RO is a type of a vector of O real numbers. LOI is a type of a matrix with dimensions O by I. So weights IO, you already know is a layer from I to O. There's no guesswork, there's no documentation needed. I didn't need to write comments here. You already know from the type that the weights IO is a weight taking you from a layer of I inputs to a layer of O outputs, just from the types alone. And just the HMatrix has the types we're using, vectors and matrices. So an R3 is a 3-vector, and L43 is a 4-by-3 matrix, and our operation is now typed using HMatrix. So you can only add vectors of the same types, right? So if you give two differently sized vectors, this would be a compile error. You can't even compile it. If you multiply improper matrices with vectors, that'd be compile error. It won't compile. The compiler helps you, and the result also is properly typed. And with this, you can actually even start doing hole-driven development, right? Because if you know you want to add something, you can leave a typed hole. The compiler will tell you, oh, you have a type hole here. What else fits this typed hole? And you can see all things that fit what's expected. So if I want to multiply a matrix with L by N by M, N by N to something vector I don't know what to use, I can use a typed hole, and Haskell will tell you what vectors are available with that shape they can use. So with typed operations, the compiler will tell you what vectors you can use are in scope, what you can use in scope, and it will enforce correctness. And basically, you gain the compiler helping you write your code. All that mystery is regained. I use typed holes a lot, so if I want to multiply a matrix with something, I don't know what I need to multiply by. I leave the typed hole, and then Haskell will tell me, oh, do you mean this vector? And it's usually the right answer. So a quick these types N, M, and N have kind nat. This is enabled using data kinds. So data kinds in Haskell enables new types and kinds. So every value and type gives you also a type and a kind. So in Haskell with data kinds, the values true and false of the type bool will now you also have the types true, false, and the kind bool. And in Haskell now, if you have the values from the constructors colon and cons and nil, you also get colons the type constructor and nil the type constructor and the list kind. Just when you turn on data kinds, you get all these useful things, have more things at the type level. So this thing here, an R3, this is the type 3 that has kind nat. So you can't put in something silly like true, or you can't put something silly like int there. There's no rint. It has the kind check. So just some more examples. The type of true is bool. The kind of true with the quote is bool. So you have the kind true with the type true with the kind bool. This is a Haskell extension that is pretty invaluable for writing type-level code. So you have the value true then false the list. But in Haskell with data kinds, you also have the type true false with the kind listed bool.
It seems to me that you're relying on the use of this type of boolean to prevent you from making mistakes earlier, like with the nat, for instance.
Yeah. So true can be used to say the same thing, and
It requires that you use this to make sure that you don't make mistakes. So it's not inherent in the data type that you had before. It's inherent in this that you're able to catch these mistakes.
Yeah. So I'm not sure exactly what I might be missing.
Your disciplined use of this type of rule to catch these errors, because if you use something else, you can.
Yeah. So true is at the type level, so the compiler can check true or false at type level. So now we can write a type network. So here's the type network. So network is now a type that takes an input size, a list of hidden layer sizes in its type, and an output size, and returns a type. Same constructors, looks a lot the same, pretty much identical, except now we have type annotators everywhere. So the first constructor will construct an output layer, with just one layer, and this has no input layers. No hidden layers. So if you use the O constructor, you give it weights, and you basically create an I to O, a single layer perceptron, with no input layers. Using our new cons, if we give a weights from I to H and network from H to O, we now get a network that has from I to O with new hidden layers H and H cons H has. So just yeah.
So I find it really interesting that the known nat constraint, you only actually need it for cons. That
yeah.
It would be it wouldn't mean anything extra if you just define.
Yeah.
It to weights.
So the reason.
Over constraining weights, or you would be over constraining the O constructor.
Yeah. So the reason why we constrain H, it's actually not necessary, but just for simplicity, we'll see later, is because when you have a generic network I, H is O, you can specify I and O at the call site, but you can't specify H individually. It's hard to specify H individually. So we'll see later how this is useful. But no nat is what HMatrix uses to do its math. So it's needed to constrain H to be a known nat number that HMatrix can use. So here are some example networks. If we have one hidden weight, hidden one layer, weights from 10 to 8, hidden 2 from 8 to 5, O from 5 to 2. If we cons them H1 cons H2 cons O, that should be big O. We get a network from 10 to 2 with hidden layers 8 to 5. And if we try to do this, it'd be type error. Again, there should be a big O before this O here. And you actually do this in GHC, GCI, if you say H1 is equal to that, type that, and maybe you call it undefined. So now we can make a chain. The chain's type is reflected in the type of network. And if we chain things incorrectly, that's a type error. questions? Everyone following so far? Yeah?
What is the known nat constraint?
Yeah. No nat is a type constraint on the dimensions that HMatrix uses to do its math. That's kind of a high level thing right now. So I have here. So HMatrix, no nat lets you reflect the type back to the value level, so you can use it in your actual implementation of the function. So for us, for now, the only usage is for HMatrix. You can think of it as an opaque thing that HMatrix uses to implement plus and multiply. You can think of it as HMatrix needs this to use it, so we have to provide it to use it at this point. Is there another question in the back? So it's just a part of the API of HMatrix for now, to us at least, at this point. So HMatrix needs the constraints, we need to provide it to use it. And then so this chain, 10 to 8, 8 to 5, 5 to 2. Now we're from 10, 8, 5, 2. And then anything else is a type error. If we had 7 here, it would also be a type error. So just the types now have to match. It's like puzzle pieces again. Running, if you notice, this is actually the exact same code. I could basically copy paste the code. The code is exactly the same, but now actually it's exactly the same. I should be supposed to change it to new types. I didn't notice, but I think this is correct in the actual the let me open the data files.
With known nat constraints on I know.
Yeah, let me open up the code to show it for real. I didn't notice this. So we have type networks HS. Yes, so now run layer. Now this type specifies now it's completely a total function at this point. It takes a weights from I to O, give it an I vector, and gets an O vector back. Total, it's total, and it's total as in not partial, is enforced. So you can't give a 3 vector to weights that expects a 2 vector. And we're here, run net, also again total. If you pass in a network IHSO, if a network you have a network 10, 8, 5, 2, like before, you can only pass in vectors of 10 elements. Only get back vectors of 2 elements in return. It also constrains the output too, which is nice. So the user knows that if you run this on a vector with I, you'll get an O out for sure. It's enforced type level. User can rely on that in doing their functions and the rest of their Haskelling. And again, the code is actually identical. If you notice, this is identical before. This is identical. So basically copy and pasted from before, except now these are used by these now enforced. These are now type aware versions. So everything here is the same, except now because of these new types, you can already these already work. These are already verified operations. So with no change in code at all, with minimal change in code, with minimal change in expressiveness, so we're just as expressive before. Our writing is no less cluttered. It's no less cluttered. It's just as clean as before. We added for free safety, type safety. And then the guaranteed lineup. Generate is actually interesting too. You can actually, like how reading Haskell is, you can have the user demand different types and give different types based on what the user demands. So actually, for the new random weights for this version, the user gives no inputs before, right? Before, the user had to give an int that tells you what dimensions they have. But because types are so strong, there is only one possible dimensions for WIO. H vector knows to generate a matrix of I to O, of O to I, and a vector of O. So now the user doesn't have to supply types anymore. Doesn't have to supply the dimensions anymore. Dimensions are now provided, now basically are given as a demand from the user. So now you can't mix up int to output. You can't actually switch I and O. it's just automatically correct, right? So if I was a user of a library and I had to make random weights, I might think that the I and the O are switched and pass them differently. And the documentation might tell me not to, but I don't need documentation, I don't care, I write anyways, and I get the wrong answer. But in this way, documentation is not even necessary. The names are necessary, the documentations are necessary. All you need is the types, and the compiler itself, enforces the documentation we had originally. So this is user proof. The user can't accidentally pass in the wrong dimensions thinking that they're switched. And there's none of the awkward issues with parameters being switched orders that Haskell often has, because Haskell has no name parameters. So you often get that problem with Haskell. But in this case, it's already demand driven already. There's no need to switch. There's no room for error. And the code here is the same too. Same code, and except now we have demand driven vectors and samplers. And HMatrix handles the rest, and the code's the same. We lose expressiveness. We actually gain expressiveness. So people say that types lose expressiveness. They make things more clunky. In this case, our types actually made our functions and our implementation more expressive, just by having the types be there at compile time. And generating it is we have a problem generating it though. Because when you generate a network, the user can demand any H's they want, right? So how do we know what inputs they want? H's is a variable at the type level. We can't pattern match on H's. Does everyone see the problem here? If we want to create a network 10.850.2, we need to know how big H's is, but we don't know, we can't match on H's. Types aren't pattern matchable at the value level. Everyone see the issue, the question? Yes?
You're talking about an array that's been made, or a list that's been raised up to its type.
Yeah, so the type H's gives you, it could be 853. So we can't match on the types at runtime. Why? Because at Haskell, types are raised at runtime. Runtime types don't exist. It's only at compile time. So we can't just match on the types like this. It's not possible. So it's actually an issue. This is an issue that comes fundamentally from Haskell being a language that has types erased. In languages like Idris and Agda, types exist at runtime as well. Bless you. So this issue doesn't come up in nicer languages, but in Haskell we have to deal with this unique issue in Haskell, which is one of the downsides of dependent programming in Haskell. But there's a solution. The solution is called the Singleton Pattern. Singleton patterns, the singleton is a type that has only one value. So if the sing bool, so a value of type sing false has one constructor, s false. The value of type, we're defining a new data type here. A value of type sing true has s true. So here we're defining a new data type. This is pseudocode. It's not exactly going to compile, but this is essentially saying that the type sing, taking a bool and giving a type, has two constructors, s false and s true. S true is type sing false, s true is type sing true. And so if I have a value of type sing true, I know the constructor is s true. And consequentially, if I have the value s true, I have the type true in my parameter. So these are often called runtime witnesses of types. So if I have a type level list, I don't know what it has, I can pattern match on a singleton representing it. And if the singleton was made with s nil, I know that it's empty. Made with s cons, I know it has items as well in it. So this is a little, if you've never seen singletons before, this might be complicated, but we're going to use them, and the questions will hopefully be more clear when we use them. But just another demonstration, the value s false has one inhabitant, is the only inhabitant of the type s sing false. The value s true cons s false cons s nil is the only inhabitant of type sing true false. And the value s nat 1 cons s nat 1 should be 2. Has only inhabitant of type sing 1. Right, this should be a 2, 1, 2. So in this case, we actually pattern match on types, right? If we have a sing h's, we can say, oh, if it's s nil, it's empty list. If it's s cons, it's a non-empty list. Well, let's see it in action. So we can make randomnet take an extra parameter, a singleton, as input. We'll pattern match on it. This is the syntax is LambdaConf syntax. I use it because I don't like thinking of new names for things, so lets me just pattern match in a point-free way. So if the singleton, so let's walk through this very slowly. So we use singleton witnessing the type h's. We want to generate network IHSO. So if singleton is s nil, this means that h's is the empty list, right? Because the only way you can get s nil is to have empty list as h's. So this means that we have an empty network. So in this branch, h's is nil. Likewise, for this one, if we pattern match and get s-cons, we know that h's is not nil. It's actually a non-empty, so there's actually more to do. So we generate the weights and the rest of the net, and then we cons them together. So everyone see what's happening here? If the singleton we give is nil, this lets us know that h's is nil. So we can just generate the output layer. Otherwise, yeah?
So you still had to pass something else in here that you were not passing before.
Yes.
Right? So why not just pass in like h's and then?
So you can't pass in h's because h's is a type.
But you can pass in like a list of something and say whether it's an empty list or a non-empty list. It's like case length of.
So the type of a list is just a list, but you can't make that reflected in the type of the output.
Type you pattern match on whether it's an empty constructor or a list with some elements, right?
Yeah, well, the list is a type level list, right? Because if I had, let me see if I can.
So you're fixing a type with a value then.
Yeah, so the value determines the type.
So why do you need to have new things when you can do the same kind of thing?
So yeah, if you pass in just a list, like a list of integers, right? The user can still pick the output h's, right? Because if I pass in a 10-item list, I can still demand a network with no hidden layers, because it does not. The types aren't. The type of your list and the length of h's aren't connected to the compiler's point of view. So if I pass in a list of ints, that list's length and the length of h's, the compiler can't make sure they match together, right? Because if I pass an empty list, I can demand h's to be a 10-item list, and the compiler will be okay with that. So the reason why singleton is that this lets us make sure that whatever list we pass in, whatever list we passed in, that list is the same thing that we put, that is the output h's. Do you have a question?
So I do get the need for the runtime witness, but could you show us a call site how do you get this runtime witness? Pass it into the function?
Yeah. So actually, well, on the one answer is you can use this. You can create this using constructors, right? So snat1 const snat1 const nil gives you a singleton with the list of.
So I basically need to know I'm about to demand a 10-element list, and I have to pass in the runtime witness so the compiler can see the value.
Yeah. So for now, it's like as if we passed in a list, but we passed in a list using weird constructors, basically. For now, but we'll see that we can make this better story. And the one cool thing is that random weights types match automatically. I think that's pretty cool. Isn't it cool that like random weights they know they match automatically? Because it just kind of knows automatically what it needs to be. It's kind of neat because you can't accidentally pass in the wrong parameters because it's determined by the compiler directly. So I think it's kind of cool. Now the problem is that it's really annoying to pass in a singleton, but we actually, if we know the type runtime, we actually make it an implicit parameter. So there's a class sing_i in the singletons library that lets you generate a singleton for a given type automatically. The automatic generation. So if I type sing, if I type sing123, it'll give me sing123. So now we can even make this better. We can have this be a constraint, and we can now basically have automatic inference of our output type. So this generates the singletons implicitly for us. So we can now get the same expressiveness, the same. We don't have to do manually. We can have it automatically for us. So using this constraint, this lets us generate singleton for us automatically. So we don't even need to write it out. Yes?
So in case Haskell would get the feature to pattern match on the type at runtime, so in this case, Haskell had to know to not erase that specific type. Singletons would be obsolete.
Yeah, if Haskell can intelligently intelligently preserve type information to runtime, singletons wouldn't need to happen. Yeah, but the reason why is because Haskell erases all types right now. And types aren't. So this lets us automatically generate on this. So now we have the same type signature before, but now more expressive. So we basically get the same API, nicer because now we have demand-driven types like before, demand-driven shapes like before. So what do we do here? We wrote an untyped implementation of our program. We saw that there's so many ways things go wrong. There's so many the implementation space. The implementation space was huge. So many ways can mess up, and the user can mess up documentation. Things can rely on documentation, rely on names, and we added types, and a lot of the issues went away. The documentations, we can't mix up params anymore. Shapes are determined for us by compiler, and the best thing is the compiler helps us write our code the whole step of the way. And I didn't include this in the slides because it's kind of long, but if we do backprop again, it's almost identical, except now it's validated. So if we compare the code here for training, the backprop is virtually identical. I think it actually is identical. You can paste the exact same code over again. It's identical code, same expressiveness, but now the compiler helps us write the code. I could have wrote a type hole here and it would tell me what needs to go here. If I wrote like a typed hole here instead of, I could have written logistic underscore, and the compiler would go, oh, do you mean Y? Because that's in scope. And actually, at this point in time, the only possible vector that can fit here in this shape is Y. So the compiler can already write code for us. The code is the same. We retain expressiveness. There's no loss in expressivity, but we gain the correctness validation, with lack of partiality, totality, and user lack of reliance on documentation. Everything is, we gain all that just basically almost for free, same expressiveness, just by adding types to our program. And I think it's a good place to end here for any questions. Yes, and before reading, I have a blog post that goes beyond this to other techniques. Yes?
Can you show us the list of extensions you use?
Yeah, so it's on there. It is not trivial. It is not trivial. This one needed, actually it's not that bad. This only comes because we wanted strictness, so it's not needed. The rest of these are definitely necessary. Oh, this is not needed either. I just write this because for syntax. We need 1, 2, 3, 4, 5. Yes, that's it. I mean, that's it. Yeah.
Did you need scope type variables outside of the type descriptions of the random?
We actually never need scope type variables. You're right. It just makes things a lot easier to write. Scope type variables actually is a funny thing. Is actually always an unnecessary extension, but it just makes things a lot cleaner in many cases. Yeah.
So I have a very close application of this technique, but there's an additional constraint, which is that in order to get to the singleton type, I essentially need to parse unstructured user input.
Yeah.
And I don't actually know at compile time how much input, how many, how many layers.
That's a good question. It's actually part 2 is actually, this blog is actually just goes into that. So if I had another hour, I would go into that. But part 2 would go how to have types appear from outside external sources that aren't known until runtime. Yeah.
What's the address of that?
At the end of the slide is, yeah. Yes?
Type literals like 1, 2, and string has 1. Can you give us a type read on this and documentation kind of looks outdated? Do you know the full reference?
So type literals are just basically an extension of data kinds, but I think the most data kinds really isn't that deep of an extension. Using it, there's a lot of implications in using it. For the most part, basically all it means is that you get a kind true, a type true with kind bool. Yeah, if you have type 1, you get if this is type 1 of kind nat. The type of like the string literal is of type of kind symbol. So it's just new types and new kinds.
Yeah, but I, for example, found it very hard to code my circumstances. Like, say I want to do a Fibonacci types based on the literal.
Yeah, it's that's kind of more general, and that's kind of more talking about type level programming.
Right, it's probably not there, right?
It's there and it's possible, but there is some ugly parts at the moment. Yeah.
Figure out how to do it by, not using literals, like basically, numbers.
Yeah.
Fibonacci on the text.
L-
But I prefer to do it in literals.
Yeah, type literals in Haskell are actually all primitive types. They have no structure, internal structure. So the types 1 and 2 are unrelated to GHC. So it's really, you have to kind of be, it's because piano numbers have structure in them. You can pattern match and go in that structure. But 1, 2, 3, those are all basically disjunct types like true and false. So it's a little tricky, but there are tools to make it workable. And you're right, when you do this enough at the high level, you do need to get into functions like that. But it's possible, and it's becoming better by the day, by the month. Yes. Any other questions? Well, thank you for having me.